Assalamualaikum and hello everyone. Welcome back to a new video. In this video, we will talk about ionization energy, where we will define the first and second ionization energy, and we will analyze the variation in the first ionization energy across a period and down a group. So on your notes, it will be on page 10. Okay, so ionization energy, we have looked briefly during our chapter 2.1. Okay, so again, what is ionization energy? Ionization energy is the energy required to remove 1 mole of electron from 1 mole of neutral gaseous atom. Okay, so it's the first one. Why does it mention about the first one? Because it is actually where we remove the first electron from 1 mole of our neutral gaseous atom. Okay, so what is the definition of the second one? So for the second ionization energy, it is energy required to remove 1 mole of electron from 1 mole of positive ion in the gaseous state. It means that, okay, so for the ionization energy, it is you must remove 1 mole of electron. So first thing first, for example, if you want to form Mg2 plus gases, okay, you have to start from scratch. You have to start from, okay, first you have to do magnesium, go to magnesium plus electron. Okay, then from the magnesium plus you can form magnesium 2 plus electron. So you can't go straight forward from magnesium neutral gases atom to magnesium 2 plus. You can't. You have to do it one by one. We're going to remove 1 mole of electron. Okay, so that is a definition for first ionization energy and the second ionization energy. Okay, so next what we're going to look at is actually the trend of ionization energy. Okay, here you mentioned that the first ionization energy depends on the strength of attractive forces between the valence electron and the nucleus. Okay, so what happens is that the higher the attractive force between our valence and our nucleus, it is harder to remove the electron. So when it is harder to remove the electron, it means that we need more energy, and more energy is needed to remove the electron, because as I have mentioned before, the nucleus itself is positively charged, electron is negatively charged. So the attraction is strong because it is it has the opposite charge, kan? Okay, so when the attraction is high, so it will become closer. So it is harder to remove the electron itself. So for example, if the attraction is weak, so it means that it is further away from each other, kan? So it is easier lah to remove the electron. But once the attraction is strong, so it means that the electron and the nucleus itself is near to each other. So what happens is that it is harder to remove, and we need higher energy. We need more energy to remove the electron. So here we're going to mention the higher the ionization energy. Okay, so we're going to look at the 3 cases. What is the factor here? Okay, but then this is the general pattern where across the period the ionization energy increase, and down the group the ionization energy decrease. Okay, so when atomic radius, we're going to look here, when atomic radius increase, so it means that the valence electron are far from the nucleus. So what happens is that when it is far from the nucleus, it is less attracted to the nucleus. So when it is less attracted to nucleus, it is easier to remove the valence electron. So dia dah further away, kan? Senang dia nak remove from picture. So the ionization energy decrease. That is for the case of atomic radius. For the case of shielding effect, so when the number of shell increase, remember shielding effect is all about our ansatz. So when number of shell increase, the shielding effect will increase. Okay, so the attraction tu is less lah sebab the shielding effect tu increase. So what happens is that the valence electron are less attracted to the nucleus. Okay, because it is further away, kan? Attraction dia tu, the attraction between the valence and the valence electron and the nucleus is weak. So it means that the valence electron less attracted to nucleus. When it is less attracted to nucleus, it is easier to remove the valence electron. Hence, the ionization energy decrease. Okay, so here is, as you can see here, the pattern for the first ionization energy. Down the group, shielding effect. Down the group, we're going to talk about the shielding effect, which the ionization energy decrease. So, yang I'm going to write down the group lah. Okay. Last but not least is the effective nuclear charge. So, effective nuclear charge, hindi kita nak ingat adalah our pizzas. And this is actually for the case across the period lah. Across the period. Okay, so what happens is that for across the period, so effective nuclear charge, when ZEF increase, so the attraction between the nucleus and valence electron pun increase. So when the nucleus is when the valence electron and the valence electron and the nucleus, there's a high attraction. So it means that it is harder to remove the valence electron. So when it is harder to remove the valence electron, so it means that more a higher ionization energy, more energy is needed to remove the electron. So ionization energy increase. Okay, so that's why kita tengok dekat sini the pattern itself for across the period, the ionization energy increase. Okay, so that's the 3 factors that we're going to look at when we're talking about ionization energy. But we're going to talk about anomalous case juga. Okay, in general, ionization energy increase across the period. Okay, because of the increasing ZEF kan. In period 2, there are 2 anomalous cases. Okay, so in this case, period 2 first, we're going to look at for beryllium dengan boron, which is group 2 and 13. Okay, so how we're going to look at it? So let's look for the orbital diagram. So for the orbital diagram for beryllium, I'm going to write down. Okay, so first 1s, 1, 2. So 2s. S, 2s, 3. Okay, and then for boron, 1s, 1, 2. 2s, 1, 2, 2p, make sure 1, 2, 3, 2p. Okay, so in this case, this is actually the orbital diagram of our beryllium and boron. Okay, so as you can see here, okay, dalam case ni memang sepatutnya it must be in sepatutnya the value the ionization energy increase lah across the period. Tapi first kita tengok yang beryllium boron ni. Okay, boron ni it has a lower than beryllium. Okay, why? B boron, Be beryllium. Okay, so as we can see here, beryllium has a fully filled 2s orbital. So I mentioned here fully filled 2s orbital, which is more stable than 2p yang ni. It's not half filled, tapi dia juga bukan fully filled. Apa lagi yang kita guna? It's actually partially filled. Partial. So here is more stable than partially filled 2p orbital in boron. So what happened is that, remember that for the case of dekat mana? Sini For the case of the orbital itself, contohnya apa ni? Half filled, fully filled. Fully filled is more stable than our half filled, and half filled is more stable than a partially filled. Partially filled orbital. But then you have to be specific lah. Which orbital? 1s, 2s, 3s, 2p, 3d. Okay. So, what happened here is that beryllium has a fully filled 2s orbital, while boron has a partially filled 2p orbital. So what happened it is actually harder to remove the electron, the valence electron in beryllium. Sebab ni dah stabil kan? So it is harder to remove lah. It is fully filled. Dia orang prefer untuk to be fully filled, but then you remove the electron, so it will be harder rather than yang 2p ni. Ada satu je kan, lagilah senang dia nak remove sebab nanti dia dapat form our stable ion tu. So this is why beryllium has a higher ionization energy than boron. Okay, so that's for the case of beryllium and boron. Now let's look for the case of nitrogen and oxygen. So nitrogen ni the valence the orbital diagram dia 1s, 1 2, 2s, 3 4, 2p, 1 2 3, 2p, 1 2 3 4 5 6 7. Okay, then for our oxygen is okay, but then here 1 2 3 4 5 6 7, here is 8. Okay, remember that it's supposed to be across the period the ionization energy supposedly increase ni lah. But then here the nitrogen is higher than the oxygen. Okay, why? Okay, so kita tengok kat sini, N ni has a is it fully filled? It's not. Is it half filled? Betul. So kat sini N has a half filled 2p orbital, which is more stable than partially filled. Partially filled 2p orbital in oxygen. So the half fill is more stable. So it is harder lah, sebab yang ni dah memang cukup stabil kan. It is harder to remove. Yang ni easiest, but nanti once we remove ni nanti jadi half fill kan. Which is it wants to be a half fill lah, which is more stable. Tapi ni dah memang half fill, but then you want to remove the electron. So it is easier. It is harder to remove. So here it is harder to remove the valence electron in nitrogen than oxygen. Hence, nitrogen has a higher ionization energy than oxygen. Okay, so this is the two cases of there are two anomalous cases for period 2. Remember, kalau anomalous ni macam yang chapter 2 kita tu kan, chromium copper. It is easier for you to write down the orbital diagram. Talking about our fully filled, half filled, partially filled orbital. Okay, yang ini kita tengok pula for the case of period 3. Period 3 pun sama juga. Gonna write down the electronic configuration. I'm just gonna copy paste yang tadi lah. Copy paste sikit yang tadi ni. Okay, and S2, S2P. But for this case around, so here 1, 2, 3, 4. So it's only 10. 2P kita, so 3S. 1, 2. Okay, is it enough? 2, 4, 10, 12. So this is actually for our magnesium. Then I'm going to do for aluminium. Aluminium, 1, 2, 3. 3P. So another one. Okay, again, for this case, the anomalous case for this is for period 3 between magnesium dengan aluminium. What we're going to do, we're going to draw the orbital diagram. So as we can see, magnesium has a fully filled, tapi fully filled apa? Fully filled 3s orbital, which is more stable than a partially filled 3p orbital in aluminium. Hence, it is harder to remove valence electron in magnesium dan aluminium. Yang magnesium ni dah fully filled kan. So beryllium pula. Here supposed to be our magnesium has a higher ionization energy than our aluminium. So betul kan yang ini part. So that's for the case of magnesium dengan aluminium for period 3. Next, for the case of phosphorus and silicon. So silicon ni, so here 3s, 3p, 1, 2, 3, 3p. So baru 12, 13, 14, 15. Okay. So here is for our phosphorus, for our silicon 3p. 16. Is it enough? Then ni 6 tu lah, 16. So in this case, phosphorus has a half fill apa orbital? Half fill 3p orbital, which is more stable than a partially filled 3p orbital in sulfur. Silicon. S ni sulfur sebenarnya. Okay. Yang silicon ni Si. S sulfur. Okay, so again, since half fill or 3p orbital is more stable, so it is harder to remove the valence electron in phosphorus rather than sulfur. That's why phosphorus has a higher ionization energy compared to our sulfur. Okay, So that's it, the end of ionization energy, where we have discussing the definition, the factors, and we have looked for the anomalous case for ionization energy.